Hi guys, Audrey here. So we have at this point pretty much finished with partial fractions. We've seen all of the four cases, we've seen problems for the four cases, and we've seen all of the forms that could show up after you have applied partial fractions. So that said, we talked a little bit about how whether or not a polynomial factors changes the level of difficulty of the problem. So what I want us to do right now is kind of look at that in terms of these two problems we have right here, and at the same time also remind ourselves of one of the forms that's a little bit more challenging that occurs at the end of partial fractions. So you'll notice these two integrals look almost exactly the same. It's ln of x squared plus 5x plus 6 versus ln of x squared plus 5x plus 7. That said, they are not the same to do. So if we look at ln of x squared plus 5x plus 6, we'll notice that x squared plus 5x plus 6 factors into two linear factors. So we'll have x plus 3 times x plus 2. X squared plus 5x plus 7, however, is irreducible. And so if we want to check that, we can remember that we just have to look at b squared minus 4ac, the determinant, that value that shows up under the square root when we're doing the quadratic formula. So here are b squared minus 4ac. That's 5 squared minus 4 times 1 times 7, which gives me 25 minus 28, which is indeed less than 0. So this polynomial does not factor. We're going to see that in order to do the first integral, it's going to take us about 2 minutes. To do the second integral, it's going to be more like 15 minutes. So really that one itsy bitsy small number difference makes a huge difference when it comes to taking the integral. All right, let's get started. We'll start with the case of when the polynomial factors. So we have the integral of ln of x squared plus 5x plus 6. And we already saw that x squared plus 5x plus 6 turns into x plus 3 times x plus 2 dx. Now, if you'll recall, we actually have a log rule that tells us that natural logs magically turn multiplication into addition. So ln of a times b is equal to ln of a plus ln of b. So what that means is if I apply this rule here, I actually end up with ln of x plus 3 plus ln of x plus 2 dx. And now I can do the two integrals separately, except really we just have to remember, I said we could memorize this. The integral of ln x dx is actually x ln x minus x plus a constant. So in this case, we don't have ln x exactly. I have ln x plus 3, ln x plus 2, but that x plus 3 on the inside and that x plus 2 on the inside, they both have a derivative of 1. And that's important because we know that when the inside function has a derivative that's just a constant, we can apply the known form that we have right here, and then just divide by that constant. So having a derivative of 1 means that we can literally just apply the known form. If we had a derivative that was a function, then we'd have a problem, and we'd actually have to go through and do a substitution. But in this case, we don't have that problem, so I'm just going to apply the known form. So I have x plus 3, ln of x plus 3 minus x plus 3, plus x plus 2, ln of x plus 2 minus x plus 2. Plus a constant. There we go. We're done. Literally 1 minute. That said, I am going to simplify this a little bit. So this is the same thing as x plus 3, ln of x plus 3, plus x plus 2, ln of x plus 2, minus 2x plus c. Final answer. Now maybe some of you are wondering, wait, where did that plus 3 go? Where did that plus 2 go? Remember that plus 3 and that plus 2. So I actually have minus 3 minus 2 if we distribute our minus sign. So I have like a minus 5 plus c. But minus 5 plus c is still just a constant. It's another constant. So that minus 5, the 3 and the 2 that we see there actually get absorbed into that constant. So they don't have to show up in our final answer. All right, there we go. We're done. Let's look at the next one. It's not going to be quite so simple. So here we'll have when the polynomial is irreducible. And we're looking at almost the same integral. We're just going to stick a 7 there instead of a 6. Okay, so because that polynomial doesn't factor, I can't apply my ln AB rule in the same way that I did in the previous question. So the question is, how do I start this integral? And the answer is integration by parts. The derivative of x squared plus 5x plus 7 is 2x plus 5. I don't have that there. That substitution doesn't work. I can't even force it to happen. There is no good substitution here, but we do have just one function that we don't know how to integrate. And we'll remember that to find the integral of ln x itself, we just used integration by parts. So same here, we're going to be using integration by parts. And this is sort of the same idea that we have behind the integral of the inverse trig functions, right? It's one function. We don't know how to integrate it. It's not a known form. So we do an integration by parts where we let our u be equal to the function itself. And so then I'll take the derivative and I'll get 2x plus 5 over x squared plus 5x plus 7. And then dv over our dv is dx. So we let u be the function itself, and that means that all that's left over to be dv is dx, and the integral of dx is x. So then I do my subtraction here, and I get that this is equal to x ln of x squared plus 5x plus 7 minus the integral of 2x squared plus 5x over x squared plus 5x plus 7 dx. So that 2x squared plus 5x came from me just multiplying my du times my v. I multiplied that x and distributed it immediately through the 2x plus 5 here. Okay, so now what we might notice is that doing that integration by parts turned this into a rational function. And when we have rational functions for which substitution fails, our go-to should be immediately we're just going to look at the degrees of the numerator and the denominator. So here my degree is equal to 1 up top, and my degree is equal to 1 on the bottom. So what that means is I should do my special division. So I get that this is equal to x ln of x squared plus 5x plus 7 minus, now I'm going to multiply by a 1/2 on the inside to turn that 2x squared into an x squared, and I'm going to multiply by 2 on the outside. So I'll get minus 2, the integral of x squared plus 5 over 2x. That 1/2 got distributed to both of my things there. And then all of this divided by x squared plus 5x plus 7. And now I want a plus 5x plus 7 on top. So I'm like plus 5x plus 7 minus 5x minus 7. And I separate so that I have x squared plus 5x plus 7 on one side and then everything else on the other. So we have minus 2, the integral, x squared plus 5x plus 7 over x squared plus 5x plus 7, then plus 5 over 2x minus 5x minus 7 over x squared plus 5x plus 7. All right. So now we've applied our special division and we have two different integrals here. That first one is 1. So we're going to go down here and just rewrite this one last time. X ln of x squared plus 5x plus 7 minus 2 times the integral of 1 dx. And then plus 2, I'm distributing that 2. I'm also distributing my minus sign. So that's minus 2 actually. So this minus 2 right here goes to both of my integrals. The integral of 5 over 2x minus 5, so that's negative 5 over 2x minus 7 over x squared plus 5x plus 7. And then we're just going to do one last step here, and this is actually really useful for this type of problem. I'm going to take this 2 and distribute it back inside. The thing is, if you have these polynomials that don't factor and you're having to do this special division type stuff, you're often going to end up with just ugly numbers. They're going to be fractions. They're going to be unpleasant. So like I noticed that if I redistribute that 2, I can get rid of that fraction in this integral. And that's going to be helpful for me later on. It's also going to be helpful for keeping track of all of the constants I end up with, because this problem is going to get a little bit bigger. We're going to have quite a few sub-steps here. So I'm going to redistribute the 2 and at the same time take the integral of 1. So I'll have minus 2x minus the integral of negative 5 over 2x minus 7 over x squared plus 5x plus 7 dx. And I just talked all about distributing that 2 and then didn't do it. Lovely. So here we will have negative 5x minus 14. And then again, just to make my life easier and to help me keep track of things, I'm going to just cancel out those minuses. I can have that minus distribute in the same way that I had the 2 distribute. So it's actually pluses. So this right here is smiley face. Now, again, I stress with this type of problem, and really with any problems where you have a lot of integrals going on, it's really easy to kind of like mess up constants. And this problem, we're actually going to have like a subintegral and then another subintegral. So I'm going to do this. I'm going to say that this is equal to x ln of x squared plus 5x plus 7 minus 2x plus smiley face. So then when I go down here and calculate smiley face, I'll remember that's exactly where I need to go back and put it once I've calculated it. So smiley face is the integral of 5x plus 14 over x squared plus 5x plus 7. And this is my favorite kind of integral. You'll remember this is one of the forms that shows up at the end of partial fractions. So it's that one where we have a linear polynomial on top that is not the derivative of the bottom, and the denominator has a quadratic polynomial that is irreducible. So this is the case where we're going to want to force our substitution. So we start off by saying u is equal to x squared plus 5x plus 7. So then du is 2x plus 5 dx. And we know that's always the first thing that we want to check anyway. Does the substitution work? Well, it doesn't. So what we're going to do is make it happen. We're going to force it. I have 5x plus 14 on the top, but I want 2x plus 5. So I'm going to multiply here, by 2 over 5. Now, if you found it easier, you could also factor the 5 out first. I'm going to multiply by 2 over 5 to turn that 5 into a 2, which means I'm going to have a 5 over 2 on the outside here. So we have this is 5 over 2 times the integral of 2x plus 28 over 5, all divided by x squared plus 5x plus 7 dx. And now I wanted 2x plus 5, so I'm just going to do plus 5 and then minus 5. So then this becomes 5 over 2, the integral of 2x plus 5 over x squared plus 5x plus 7 plus 28 minus 5. So that's 28 minus 25 over 5. So that's plus 3 over 5 over x squared plus 5x plus 7 dx. So we forced our substitution to happen. We used our special division techniques, and we were able to separate this into something where the substitution works. So we're going to have a ln. And then that second thing we're going to remind ourselves is an arctan. So we'll see that in just a second. So then here, I'm going to separate this into two integrals. This is 5 over 2, 2x plus 5 over x squared plus 5x plus 7 dx. That 5 over 2 distributes. So I have 5 over 2 times 3 over 5, the integral of 1 over x squared plus 5x plus 7 dx. And now we're going to call this one right here star, and we'll call this one right here heart. And we can see that this is equal to 5 over 2 times star plus 3 over 2 times heart. And that way, after I've done both of those integrals, I can come back and remember I didn't bring those constants with me. I still have to multiply by them. And that way I won't accidentally forget to bring a constant back. So let's do star down here. And I'm leaving a little bit of space so that I can write my answer for smiley face when we're done. So star, we're using this substitution that we had right here. And we can see that this turns into the integral of 1 over u du. That 2x plus 5 was my derivative, so that 2x plus 5 dx, that's my du. So I have 1 over u du, which gives me the natural log of u plus c. So we get that this is natural log of x squared plus 5x plus 7 plus c. And now for heart, we have that quadratic trinomial. Nothing else works. So we want to complete the square. So we're going to complete the square here to have x squared plus 5x plus 7. Remember, it's our middle term that we divide by 2. So this is x squared plus 5x plus 5 over 2 squared plus 7 minus 25 over 4, which gives me x plus 5 over 2 squared. 7 over 7 is 28 over 4, so that's plus 3 over 4. And assuming that polynomial is actually irreducible, then you should always get a plus sign right there, because it's always going to turn into arctangent. If, however, it is reducible and you find yourself here because you didn't do partial fractions, then you'll get a minus, and it will be the other 1 over 2a ln x minus a over x plus a known form. Okay, so that said, that turns heart into this integral. 1 over x plus 5 over 2 squared plus 3 over 4. But I'm going to write that as root 3 over 2 squared so that we can see our a here is root 3 over 2, and that this is just arctangent. And again, I don't have to worry about doing a substitution because the derivative of the thing that I have there, that x plus 5 over 2, the thing I have instead of x squared, I have x plus 5 over 2 squared. The derivative is 1. So we can just apply the known form and divide by 1, which is really the same thing as just applying the known form. So this is 1 over a. So that's 2 over root 3 arctan of x plus 5 over 2 over root 3 over 2 plus c. So I am going to, on the inside here, multiply by 2 over 2 to get rid of that complex fraction. In other words, I don't want to have a fraction inside of a fraction. It's not okay to leave our answer that way. So we're going to multiply by that 2 over 2 to get 2 over root 3 arctan of 2x plus 5. Notice the 2x plus 5, it was my du, over root 3 plus c. Okay, so now we have star, now we have heart. We can go put them back up here. So we get that this is equal, actually I want to make sure I have enough space. I'm going to do it over on the left side here. So this is equal to 5 over 2 times star ln of x squared plus 5x plus 7, then plus 3 over 2 times heart, so that's 2 over root 3 arctan of 2x plus 5 over root 3 plus a constant. And then we're going to cancel out those 2's there. This right here is smiley face. So this is what smiley face is equal to. which means for our final answer, we're now going to take that and go stick it back into our original thing. And I know exactly where that goes because I had that equals to x ln x squared plus 5x plus 7 minus 2x plus smiley face. So I know that that's where that's going to go. And I'm not missing any constants. I don't have to multiply it by anything. I kept track of everything in a really concise way. It is so easy to get lost with the constants in these problems. So you've got to be really careful about that. So here we have x ln of x squared plus 5x plus 7 minus 2x. And I easily see I'm not going to mix up my minus. It's plus 5 over 2 ln of x squared plus 5x plus 7 plus 3 over root 3, which FYI is the same thing as root 3. Arctan of 2x plus 5 over root 3 plus a constant. And that, my friends, is our final answer. So, as kind of gross as this is and as ugly as those constants get, I actually really love these problems. Okay, so let's just briefly summarize what we did. I want you guys to take a second, think about it, maybe pause the video if you need to. What happened here? Let's summarize. So we said, oh, hey, look, there's a line. I can't factor that inside thing. So, well, I guess I just have to do integration by parts. So I did some integration by parts. And that integration by parts resulted in a new integral that was a rational function where the degree of the top was the same as the degree of the bottom. So we needed to do special division. So we applied our special division. And applying that special division resulted in a new integral that was one of the forms that shows up at the end of partial fractions that we learned. That's when we have a linear polynomial on top and a quadratic polynomial on the bottom. So we said, let's go off to the side and do that. We know that our technique for doing that is force a substitution in the same way that we do special division. So use the same techniques, have two integrals, one of which the substitution will work for. So that one will be a ln, and the other of which will have to complete the square, and it will be an arctan. So we found our u, we applied our techniques to force that derivative. So then we ended up with that integral 2x plus 5 over x squared plus 5x plus 7, our star. We applied the substitution, we got our line. We ended up with heart, we completed the square, we got our arctan. And then we moved that back up to the rest of the answer that we'd gotten from the special division and the integration by parts. So, as you can see, the first problem here, when the polynomial factors, was like a two-liner so fast, if you remember the integral of ln x, it's like 1 minute. When the polynomial is irreducible, it changed a lot. So it's always really important to pay attention to that, not just in these ln problems, but also in partial fractions. If you can factor the thing, then you should be factoring it. It will make your life easier. Hopefully you believe me after this. That said, even if it doesn't factor, yes, the problems are hard, but they're also fun, right? Okay, all right, that's it, guys. Bye.